Yeah, so thanks for coming again. We resume our seminar after the end of the April, and each of us are quite busy, so we just offered a meeting during May. So today I'd like to share the framework of the seminar and the contents that we'd like to study together. And I'd like to make sure that this is the informal seminar in a sense that not only covering some of the topics in detail, we'd like to share some of the topics that we can really initiate some research either individually or together. And so if some of the idea seems like a really like the sensitive to make the progress, I'd like to off the record, or at least I won't edit the recorded like the file so that nobody can take our like the original idea if that seems really necessary. But anyhow, I'd like to split the discussion into two pieces in the natural way. One is we need to study some important topics in complex geometry. That's one thing. But if it seems useful for conversation in doing research, then that's also good with me. But if necessary, I'd like to just edit the recorded file so that nobody can take our like original contribution for that. So far, we have discussed the following topic. Press the share. So if you just look at my website, so we just look at the basic framework of Taylor geometry. And I don't at this point want to review just repeat the same like the framework in a sense that if we have a concrete like the framework, I mean the setting, depending on the topic, then we will just repeat the same like the framework. In that sense, you can just review. Of course, you can look at the note and also the recorded video, but we at least talk about the basic framework in a sense. Let me just write down just a notation. So we have a smooth manifold and we have a complex structure. I want to explain anything at this point. So I assume all of you already know this. And this G is the Hermitian metric satisfying the comparability condition, meaning that G of xy equals G of jx with jy. So that, so of course, this is the case for the rear section of the rear cotangent like the bundle. So that from here, we have a triple M, J, and G. Mj and G. And from here, we define omega, which sections we just define in this way. Not just this guy, but we just encode the complex structure here. And we said this is either the fundamental form or the Kähler form. Let me simply at this point call the fundamental Kähler form in a sense that most of the time we might not consider the non-Kähler cases, even though some of the cases would be matter. So that we say it is Kähler if d of omega equals 0. So that was the condition. Is that okay with you? So this is just a basic, just a framework. Of course, this is very important. And well, so under the Kähler assumption, I also want to make sure that under the Kähler condition, this guarantees that the Chern connection, which is a unique connection that is comparable with the complex structure, coincide with the Leibniz-Bita connection. So if you already know Riemannian geometry, then you can just proceed the same calculation on the complexified tangent bundle or holomorphic tangent bundle, or so it's just the same. So yeah, those are just the basic. And I'd like to think about the classes of the complex manifold today that so with this framework, so we need to talk about the model spaces in Kähler geometry to classify the classes of each like the complex manifold, including the bounded domain and pseudo-convex domain and sterilized type manifold and so on. So what are the model spaces? Of course, depending on the context, but the most like the default like the setting would be either CPN or CN or the complex hyperbolic space or just a unit ball in CN. So this is called by complex projective space. This is just a complex Euclidean space. And this is a complex hyperbolic space. And as we call it bimodal spaces, so we assume these are topologically simply connected. So if that's not the case, then we need to take the quotient by the automorphism group. But as long as we consider the model spaces, then we usually assume to be simply connected. Otherwise, we need to specify what that means for the model. So what's the reason that we treat these three spaces as a model? So now let me share my note. So the reason is comparison in Riemannian geometry in the following sense. So this is the note I shared. And if you just go to the framework of the curvature, so let's just assume as long as you have a concrete Kähler metric, then you are able to proceed the calculation in local coordinate. Let's just assume we just need to figure out if that's really like the handy and necessary. And in such a case, I just want to jump in to the specific form of the Kähler metric. So for example, so I don't want to explain the definition of the CPN. So if that's necessary, just try to figure out by yourself and we can discuss. So we have a CPN, complex projective space. In such a like the space, we define the so-called the Fubini's to the Kähler form in the following way. And this is a very concrete like the form like this in the local coordinate. So this is the form of the Kähler Fubini's to the metric. Fubini's to the metric. So what's the specialty of this like the metric? So one is this one. Another one is this guy. So this is we call it by the Poincare metric. And in the case of the unit ball, we know this coincide with the Kobayashi metric and the Bergman metric, Kähler-Einstein metric up to the dimensional constant. So what we need to ask is why these metrics are and those spaces are special. So the reason is the following. In differential geometry, so the reason, so it's based on the comparison of Riemannian geometry and complex geometry, let me say Kähler geometry. So what's the difference? Let me say it this way. So if I just make the table this way first. So let's say this is the word of Riemannian, this is Riemannian word. So this is usually defined over weirds, and this is Kähler word. So positive curvature, zero curvature, and negative curvature. So what's the model of the positive curvature in Riemannian geometry? It's a sphere. It's a sphere. And Kähler word, this is projective space. Zero curvature or Euclidean spaces. If you have any questions, let me know. Of course, over real in general. And this is still the same, the Euclidean space here. And this is real hyperbolic space. Or you can just assume this is just a ball in Rn. This is complex hyperbolic space. So what's the difference? Meaning of the curvature is different. So in this word, we consider so-called the concept of sectional curvature. And some of the classical textbook call it by the Riemannian sectional curvature, but I think this is more common to call it by sectional curvature. This word is called so-called the holomorphic sectional curvature. So there's a difference of the being constant regarding the sign of the curvature. What's the definition? So in the word of the Kähler, we already make the same connection to proceed the derivative of the vector field. The sectional curvature is defined as a curvature tensor of x, y, y, x divided by the area generated by x and y for each two vectors. This is the definition of the sectional curvature. This is the generalization of the Gaussian curvature of the surface, so that intuitively speaking, sectional curvature means you fix two vector fields. It generates a two-dimensional, like a subbundle, two-dimensional subbundle. If you just look at the corresponding submanifold, this is just a surface. And if you just calculate the concept of Gaussian curvature, this just match with this formula. This is one that's an intuitive explanation, even though the formula seems highly non-trivial. This is one thing. What about the holomorphic sectional curvature? It's different. So holomorphic sectional curvature. So let me also use the sort of the standard notation. H as C, and it only takes X. It only takes X. Then this is defined completely different way. So still we use the same curvature tensor R. So we take X, and we didn't fix another vector field, but we know how we can generate the independent direction. And the curvature convention is slightly different. So here, those two match in Riemannian geometry. We need to make xjx, xjx. And the denominator is also slightly different. Denominator is defined as a norm square with the degree 4, order 4. So this is also the generalization of the Gaussian curvature, because so if we look at the Riemann surface can be interpreted as two different ways. Riemann surface, two-dimensional manifold over real, but over C is a one-dimensional complex manifold. So this J X to generate the additional direction, so we just need to fix just one direction in the complex world. Whereas in the real world, we need to fix two directions. So the reason why models are different is that, so for the Riemannian world, sectional curvature should be constant. And under simply connected condition, there are only three possible like the spaces under also the complete condition of the Riemannian manifold. And Kähler world, we set up the model space that constant holomorphic sectional curvature. And if that is simply connected, then there are only three cases. So for the CPN and complex hyperbolic space, sectional curvature is thereby no constant, but still is satisfy the same sign condition. So I'd like to just repeat. So when we talk about the curvature, the word of the Riemannian geometry and word of the Kähler geometry are different in a sense that when we talk about Riemannian geometry, we talk about sectional curvature. When we talk about the Kähler word, we talk about holomorphic sectional curvature when it is constant. And the Kähler word and the Riemannian word, each curvature quantities are not constant. For example, I cannot simply say so, but if the complex like the structure is defined, still holomorphic sectional curvature is not constant for the Riemannian models. So any other questions so far up to here? So if there's no question, I wanna just say big results in Kähler word. So geometry concerns the classification. So first result regarding CPN. So for this result is usually at this point called by the Frankel, Harshun, at this point theorem. So done by Siu and Yao. So this statement says the following. So you have, let me now at this point just call just a pair for the Kähler manifold. So you start from compact Kähler. And by the way, this is also a Fields method result, by the way, this is very important. So Kähler manifold with bisectional curvature. Bisectional curvature being positive. So here bisectional curvature is defined as a two vector fields is defined as a R x jx y jy divided by norm square of the vector field x, norm square of vector field y. So if you take same x and y, this generalizes the holomorphic sectional curvature. If this is positive, then M omega is biholomorphic to CPN. Of course, provided this n manifold has a complex n dimension with the Fubini dimension. So this gives the rigidity classification result so that we can characterize the positive curvature case by only looking at the bisectional curvature positive condition. It does not even need to be constant. Actually, it's not possible to be inconstant for bisectional curvature for CPN with the Fubini student metric. So that this gives the characterization which Kähler manifold becomes CPN. So this case is done. This case is done. And for zero curvature case, I don't think there's a special name of it, but still, I think it's fair to call it by also Xiu and Yao theorem. Xiu and Yao theorem. So this is the application. I want to put emphasis because in this seminar, we need to set out which topics should be worthwhile to learn together. This is the application of Hermander's L2 estimate to establish this result. So this result says the following. So M omega is complete, non-compact, simply connected. So our condition match with Cn, Kähler manifold, whose Riemannian sectional curvature decays faster. It looks a bit fancy, faster than the curvature of Poincare metric. This is a condition. It can be more like described in the quantitative way, but I want to just say that just a sectional curvature condition satisfy a little bit faster condition than the hyperbolic like the case. Then by using the Hermann's L2 estimate, so it was proven that this is biholomorphic to Cn with just a standard metric. So all those are the result of the early of the 80s, by the way. And the second result is the very important application of the Hermann's L2 estimate in the manifold setting. So the idea is how to establish such a like the biholomorphism from the reference Kähler manifold to the Cn. And in order to establish that the biholomorphism, both curvature condition and also the, what should I say, the curvature condition should be used in Hermann's L2 estimate case. So if I just go back to the table, geometry concerns the classification. And for the positive curvature and zero curvature in this world, these are already solved. We know the characterization in terms of the curvature. Is that okay with you? Yeah, go ahead.
Does this classification completely exhaust the like all domains in CN? Like where does the
That's the next the story I'd like to tell. The answer is no.
Okay, okay, thank you.
Yeah, that's why we want to look at the negative curvature.
Okay, okay, thank you.
Yeah, sure. So yeah, please interrupt if you have any comments or questions. But here I just want to first talk about, of course, the positive curvature itself is very important in all other like the direction of the conjectures. And also the zero curvature, including Calabi-Yau manifold, is also very important. There are many important like the questions in that territory. But in terms of the characterization with the curvature, positive curvature and zero curvature, there's already big result. So now let's just make the conjecture. So the now issue is, what about negative curvature? So in order to make the reasonable statement, let's just look at complex hyperbolic space with the Poincare metric. And let me just make the form of the Poincare metric. And I just want to also make sure, by the way, this because even though this is very trivial, so complex hyperbolic space, one of the model is just nothing but the Ball model, Poincare Ball model. So as I said, this is very clear. And the Kähler metric is written as I to the bar of log of 1 minus C norm squared of the negative one, like this. So we have a Poincare metric, and the Holorov sectional curvature of the Poincare metric is the same as -4 over n plus 1, if you calculate. So let's just accept all of these as just a fact, even though this is a very exercise to really check. So if you look at this guy, so you can see that this space is non-compact. It's clear. There's no ideal boundary, but this is still complete. So there's no hole, meaning that Cauchy, like the sequence, all converges in the interior, right? With respect to the Poincare metric, I measure this distance. And as long as this like the value is constant negative, being negative, is clearly negative. And from here, it's not hard to really see that Riemannian sectional curvature is, in fact, if I just call it by just a Cn constant depending on C, then this is between Cn and 4 times Cn. This is also some of the like the fact. So Riemannian sectional curvature is not constant. However, so if the Holorov sectional curvature is constant, then it is between Cn and 4 times Cn. That's just a fact from the curvature like the tensor. Let me just quote the result. So Riemannian sectional curvature negatively pinched. So this is what we know regarding complex hyperbolic space. Then what should be the theorem we need to prove? So weak conjecture is established more than 5 decades at this point. There's no result. So what's the statement? So let's start M omega. M omega. So this is complete, non-compact, simply connected. Okay, Kähler manifold, whose Riemannian sectional curvature is negatively pinched. So if you just compare with the setting of the complex hyperbolic space, each conditions are coming from the property of this like the complex like the model space. What do we want to prove? So let me just show you these two again. For CPN, so the characterization, if it have a compact Kähler, so CPN is compact, so it's necessary to put compact condition topologically. It's compact Kähler manifold with bisectional curvature being positive. There's no other space except other than CPN. So we already have this big result. For CN, so it just requires the curvature decay condition better than the Poincare metric because the zero curvature is different from the negative curvature. That's fine. And still we have a characterization as an application vector estimate. What do you expect over here? Then this M omega is biholomorphic to what? So it could be very ambitious that you'd like to say this is same as this guy. Does that kind of make sense to you? But this could be so strong. So because nobody was able to prove, so that one should weaken this just the result. So people like to say this is biholomorphic bounded domain in CN. So it contains a complex hyperbolic space. But now you see, because there are lots of classes of the bounded domains, this is a little bit subtle. But even this is the case, let's just assume this could be the case. Eventually, some of the mathematicians, including any of you, might prove this big result. Let's just assume that's the case. Then this particular means what? In particular, there exists non-constant, bounded, holomorphic function on M. Because if this is by holomorphic to bounded domain, then projection is holomorphic map. So there are plenty of the non-constant bounded holomorphic functions. Are you agree? This does not behave as a Liouville theorem of the complex analysis any longer. If entire function exists, then it must be constant. However, now if this conjecture is satisfied, is confirmed, then this must be the case. So what do we know? No idea. No idea. Any of the result wasn't confirmed. What I'm saying is senior, like the complex geometers attack this problem more than decades, and really tiny little progresses were made with after serious attempts. This is very difficult, like the questions. And with this perspective, I want you to appreciate the form of the character ripen metric. So even you already know the definition. So just as a recall from the very first, like the time of the seminar. So given, recall that, given a complex manifold, so it doesn't need to even require Kähler. So complex manifold, let me say M. So what is gamma sub M? So it fixed the point, and it also requires let me write down the standard notation that I already used. So that's a section of the harmonic tangent bundle. So that this was defined by what? So it was defined as a supremum, if you remember that, supremum of what? So we just take or what? M to D. D just means the unit just the disk. And we require this to be holomorphic. Make sure that this definition already requires the bounded holomorphic function because the codomain is D already. If this exists, then it must be bounded holomorphic function. And P maps to the origin. But this condition is just actually nothing because such a like the metric is invariant under automorphism. We can always just compose by Möbius transform. This condition is actually nothing. So we just take the push forward with this like a vector and take the just a like the norm. That's it. So this is Cartesian metric. Or expert usually call it by Carter-Weifen metric. So just a look at this condition. So now let's just try to combine with the implication of the big conjecture. Just a look at the big class. So we start from complete non-compact Kähler manifold whose Riemannian sectional curvature is negatively pinched, say from -4 to -1, for example. If this is bounded domain, then there must be non-constant bounded holomorphic functions. Is that okay with you? If that's the case, Cartesian metric cannot be essentially zero because it's defined as a supremum of such like the choices. No result. So as far as I know, some of the partial result was given in my math NLM paper that Alan knows. So just a very like a tiny small result in that like the paper. So my like the research was initiated to make the progress on this big conjecture. When I did my first like the research in my PhD program in my second year, my advisor Daminu, I asked him, so which direction should be worthwhile to investigate for my own research? He said, so it's good to look at this conjecture. And if you make any progress in this conjecture, you can graduate. I had a tiny little result in this direction. Still, at this point, I spent around or almost like the decade, and I kind of give up to really make the importantly meaningful like the progress. But in this like the seminar, I'd like to reinitiate the atmosphere of doing this like the direction of the research. So if this like the theme is like the interesting to participants, I'd like to talk about this conjecture a little bit further and try to explain which tools are worthwhile to like the look at the details to like the get a certain like the estimate eventually. Is that okay with you? Any other like the opinions up to here? So I think you understand all like the big picture of what I want to talk about. So in terms of the characterization, so positive curvature and zero curvature were already made but no result in negative curvature. and no result of the partial result regarding the existence of natural morphism, no result in terms of the invariant matrix. So even for the so if you are already expert in like the studying bounded domains in Cn, it's even hard to study Cartesian metric on the bounded domain in C1. So this is kind of crazy, but this is very like a good direction to investigate further. That's what I want to tell. Then how can you take this like a problem? That's next like the story I'd like to tell. So any other questions or comments up to here? Is this looks interesting or no? I don't know. So now I think you can appreciate this the following theorem that I tell you in the email. So theorem. This is quite recent, published around 4 years ago in here. So done by my academic advisor, Daminu, and Singtong Yao. Let's appreciate this result. So let's start from M omega. So put all same condition. So this is complete, non-compact. Just like imagine the complex hyperbolic space, simply connected. And Riemannian sectional curvature is negatively pinched. Or the same, or the same. Is it okay with you? So what they obtain is the following. So there exists complete Taylor-Einstein metric. There exists Bergman metric. There exists Kobayashi-Royden metric. I want to talk about the definition at this point. Please imagine with the conjecture that I share the spirit. So let me use this notation. For algebraic geometry, I should not use this notation because this usually represent the Euler characteristic in that field, but I usually prefer to call just denoted by just chi. So such that satisfy omega, this reference scalar metric, omega sub ke, omega sub b, chi sub m are uniformly equivalent. And this constant, this means, i.e., there exists constant depending only on curvature range and the dimension, such that each metrics are related in this sense for all those metrics. So in the complex, like the geometry community that I discussed with the senior, like the complex geometers, this is regarded as one of the deep result. So if you just appreciate the implication, if you just imagine with this complex hyperbolic space with the Poincare metric, we know Poincare metric coincide with the complex Kähler-Einstein metric. We know it coincide with the Bergman metric. We know it coincide with the Kobayashi-Royden metric. And also we know it coincide with the Cartesian metric. And in this framework, at least they induce the same topological structure, equivalent condition, but it does not, of course, guarantee they're exactly the same. This is kind of reasonable, right? In this abstract framework. However, what is missing? Cartesian metric in this statement. Cartesian metric is missing. Why? Because we have no idea whether or not there is a bounded holomorphic function. So that's why we cannot tell. And what do we also do not know? We have no idea. So this resembles the situation of the reasonable bounded domains in Cn. So for example, if you look at the squeezing function, so the squeezing function, positive squeezing function implies that all four invariant metrics are equivalent from one to the other. So in this statement, there's no squeezing function in this like the statement, but three invariant metrics are equivalent with the reference scalar metric. So this is very similar. And this is sort of the expectation. Is that kind of make sense to you? So still, this does not solve completely regarding this big conjecture, but this is very relevant. So with that perspective, I'd like to tell two things. One is the implication of this theorem. This theorem itself is already interesting enough, in my personal opinion, to look at the detail. If you want to establish either the comparison of the equivalence of invariant metrics, I think this is very good, worthwhile to study in detail. And in my like a PhD program, so this is my primary reference to look at always to imagine what should I do. So this is one thing. The one implication of Wu-Yao result. So now let's just look at the big conjecture again. So let's just assume we already have this. So with this class, so M omega is conjecture to biholomorphic to bounded domain in Cn. Is that okay with you up to here? So if we look at this result, what do we know? We have actually further information. So this theorem says that there must be complete Kähler Einstein metric. According to this theorem implies that at least there must be complete Kähler Einstein metric. Are you with me? That is guaranteed. So we didn't have that information in this statement yet. Then what we know is the result of the NMOOC professor in Hong Kong University. So given a bounded domain in Cn, given in bounded domain in Cn, so let me call it this by omega. This omega admits a complete Kähler Einstein metric if and only if omega, what do you expect, is pseudo-convex. I mean, weakly. So that Levi form appears. So let me just repeat. So if bounded domain in Cn admits complete Kähler Einstein metric, then such a bounded domain must be either you can call it by domain of holomorphy or weakly pseudo-convex domain. And in this statement, there's no boundary regularity in this statement of the characterization. Is that okay with you? So this is also a big result of the Professor Moog. Yeah, go ahead, Jasmine.
Yeah, in that big conjecture, why do we hope that to be biholomorphic to the bounded domain?
So the reason is coming from the model spaces of the Kähler geometry. So yeah, thanks for asking such a like the intuitive like the question. So we'd like to, so first we have the model spaces of in Kähler world, either projective space or Cn or complex hyperbolic space. So all those spaces satisfy the constant Holomorphic sectional curvature condition with the corresponding signs. And in that case, the Riemannian sectional curvature is pinched. So that's what we know for these models. And what we know is for the positive curvature and the zero curvature, so there's already big result that the curvature condition indeed characterize the Kähler like the models for positive curvature and the zero curvature. So that is especially if you look at the statement of the Cn, it only also requires the curvature condition, and we just replace the curvature condition to be negatively pinched Riemannian sectional curvature condition that is satisfied by the complex hyperbolic space. So it is at least, so people in old generation believe this is reasonable to believe it is biholomorphic is like essential in Kähler world, right? Complex geometry is just in terms of the biholomorphism, up to biholomorphism, right? So that if there's a biholomorphism, we just treat them as the same. So that we just want to treat Kähler manifolds biholomorphic to complex hyperbolic space as the ideal situation. But this could be so good. So just people weaken the implication that it could be biholomorphic bounded domain. It's kind of desperate in my opinion. Is that kind of okay with you. But what I said is that as long as bounded domain admits the complete Kähler-Einstein metric, then it must be weakly pseudo-convex domain. It could be strictly pseudo-convex, but there's no guarantee. It just guarantees the weakly pseudo-convex domain. So Levy form on the boundary might have a zero eigenvalue. We can say so. So, and if you now combine with this result, same setting of the conjecture, and it admits the complete Kähler-Einstein metric. So therefore, you can strengthen the implication. If this is the case, what do we know? We know this. Let me just rewrite with a different color. So if this conjecture is correct, it must be at least weakly pseudo-convex domain. Because we already know there must be complete Kähler-Einstein metric. Does that kind of make sense to you?
Yeah. Thank you.
Sure. So
Just adding to his question,
sure.
are there example of bounded domains which are not biholomorphic to be in satisfying all the necessary conditions?
Or the necessary of which one, for example?
Okay. Just in the above, and the same question that Joseph asked here. Instead of telling the model space, we expanded it to bounded domain in CN. And the question is, are there bounded domains which are not biholomorphic to BN with the Riemann and sectional curvature being pinched between, like negatively pinched, unbounded?
Thanks for that question. So in fact, that's my very first paper that you already actually saw. So let me explain that. So, in fact, so let me just go back to this, like the theorem, this conjecture. So so this is the implication. So what my advisor shared me when he posed this, like the Wu-Yao theorem. Actually, it was posted on 20, like the 17, if I remember it correctly. He was actually thinking in his manuscript with Professor Yao. So what he thought is that, in fact, this conjecture should be strengthened to bounded strictly pseudo-convex domain. There's a reason. So the reason is the following. So this is an imagination. So what we know is if omega inside of Cn, so but at this point for the experts, that may be very precise. So this boundary condition must satisfy C4. C4 condition for using Clambeck's, like the result of the cross-section curvature program metric. In order to do so, this was the imposed. So if omega is strictly pseudo-convex, let me now use our like the brief like the notation at this point, then omega sub ke, omega sub ke, omega sub b, Kobayashi, Carl Theodori are all uniformly equivalent. This is the combined result with the, so yeah, let me skip to write down the full name of the author. I'm afraid of like the writing the wrong, like the alphabet or the like the important like the people. But so this like the result, so this is around the, if I remember correctly, around the 778. So this result implies it matched with the Wu-Yao theorem. According to Wu-Yao theorem, three invariant metrics are equivalent from one to the other with the reference Kähler metric, and this is similar to the known result of the C4 strictly pseudo-convex domain. And also there is a counter examples. Especially these examples are bounded domain in C3 that is finite type. That Bergman and Kobayashi are not equivalent. As far as I know, there are two concrete examples satisfying this counter example condition. So finite type, so this is not strictly pseudo convex. So therefore, we already know from just combining known result that for the weakly pseudo-convex domain, including finite type in C3, invariant matrix does not need to be equivalent in general. For strictly pseudo-convex domain, they are equivalent. Therefore, what they first thought is that as long as invariant metrics are equivalent, of course, there's no Cartesian metric here, and we know the nature because we have no idea how to prove the existence of bounded Holomorphic function in this like the framework. However, this like the case, the class would be in fact turns out to be bounded strictly pseudo-convex domain. That was reasonable. However, this was not the case. So now let me just show you my very like the first paper that Ellen actually saw a long time ago. So because of that reason, there was a chatting. Who proposed the big conjecture? Yeah, that's actually a good question. I tried to search all like the literatures before when I did like my like the PhD. So I think the primary like the reference should be the problem list of the differential geometry proposed by Professor Yao. So there's a famous like the conjecture list by Yao, done by Yao, and there's just a corresponding like the statement. But it's not exact precise state in this way, but this is very well known among the experts. So when I just go to the Confluence Geometry conference, I usually talk about this conjecture. Everyone knows it, and everyone actually wants to solve this problem. So Ellen might remember this like the paper. So with the Bergman Connor explicit form. So this is actually the counter example of what I already said. So look at this like the set. This is many people call it by the either ellipsoid or Tulin domain or egg domain. There are many different like the names for the representing same set. So there are two parameters M and N, and M and N just is for the dimension, and there's a parameter P in this order. And if it's P equals one, this is just a complex hyperbolic space. If P is not equal to 1, this is something different, something else. So what I show here are several things. So just look at this conjecture. This correlate, this consequence. There exists simply connected, weakly but not strictly pseudo-convex domain in C2 with Riemannian sectional curvature negatively pinched with respect to Kähler-Einstein metric. But still, invariant metrics are all equivalent. And by the way, it only says 3 invariant metrics: Bergman, Kähler-Einstein, and Kobayashi-Royden metric. So still, you might think, well, Cartesian is missing here. It is not. It is not missing in a sense that if P is greater than or equal to 1/2, this is convex domain. Then what do we know? We know Lampert theorem. Convex domain, we already know Kobayashi and Cartesian are already the same. So this is the example, which is not strictly pseudo-convex domain. One can check just investigate Levy like the condition, Levy form condition, and then at least we know that it does not need to be the strictly pseudo-convex domain. So this satisfies all condition of the big conjecture. This is complete, simply connected, non-compact, whose Riemannian sectional curvature is negatively pinched, but not strictly pseudo-convex. This is weakly. Is that okay with you? And I just confirmed this just from the elementary calculation with the explicit form of the Bergman Connor. So that's it. And let me just now go back. All right. So then what do we need to see? So still Cartesian metric is missing. And even we show the existence of bounded Holomorphic function, it does not mean the reasonable estimate of Cartesian metric. We do not know still the existence of bounded Holomorphic maps. We do not know if that's the case. We do not know how to estimate the Cartesian metric reasonably. We do not know how to establish a comparison I mean, yeah, the equivalence with the character metric with other invariant metrics, we still do not know how to establish this most like the big like the implication we'd like to prove. How do we prove such a like the class is by holomorphic to bounded domain in Cn? So this is most like the important like the one. So why this conjecture is interesting in complex geometry? Well, when we talk about mathematics outside of even complex geometry, so mathematics concerns the set with the function with the net reasonable structure. So in the negative curvature case, we still do not know how to talk about the set, I mean the object. We still do not know how to deal with the natural morphism. Let me say in the abstract like sense, in the like the category of the complex manifold with the negative curvature. So these are the natural like the objects with the morphism. We still do not know even for the most like the natural like the objects and the natural morphisms. So equivalently speaking, so there should be new perspective to investigate anything further. So in that sense, this is interesting. So what I'd like to tell at this point is not the implication any further, but you might wonder, so how they prove this like the theorem. I'm not talking about the story. I'm not talking about the like the proof argument. I'm talking about the tools. So this theorem, so the way they prove is they knew this guy. So this result of the Cn was the consequence of what? Hernandez error to estimate. So that this is just the application, also application of error to estimate. So that they just use the error to estimate in a very clever way with a different curvature condition to say so-called quasi-bounded geometry. I will not talk about the definition. So they establish quasi-bounded geometry from the application of the error to estimate. So let me just talk about the big story. So the how they came up with their results. They just look at Hernandez error to estimate first, because they knew they can at least compare with the zero curvature case. Then they show that quasi-bounded geometry, they show whatever definition is. So quasi-bounded geometry. First, so why they wanted to show? So if they guarantee this condition, quasi-bounded geometry, this condition, then this guarantees to establish the Monge-Ampere equation in non-compact setting. So this is really like a crucial. So in non-compact setting, so in order to solve the Monge-Ampere equation of the Calabi conjecture, so in fact, compactness plays a crucial role, truth be told. And in the non-compact setting, just the Hilbert space is not in analysis, does not establish in the nice way in general. However, under the additional assumption of the quasi-bounded geometry, this guarantees to establish the correct setting of the Monge-Ampere equation. Monge-Ampere equation means both Taylor-Rich flow and also the original argument of Calabi conjecture. Both. So then this guarantees to control Taylor-Einstein metric. And others are just the byproducts. That's the basic idea. So what they did is they just look at the error to estimate first. And error to estimate guarantees quasi-bounded geometry. Quasi-bounded geometry made them enabled to handle complex Monge-Ampere equation that was used to control the Taylor-Einstein metric. That was, and others are just the byproducts. That's their idea. And they was able to do so because they already knew the result of Xiu Yao in the zero curvature case. That's the base, very, very nice, I like the idea. So in order to understand their like the proof to establish the comparison or equivalence in matrix, so this is now needed to study. This is now needed, and also this is also needed. At least these two are really crucial to study complex geometry outside of this like the theorem and B conjecture even. So that's why I'd like to proceed this like the seminar in the following way. So if any of you want to like present some of the like the topics regarding complex geometry or like the several complex variables, I'm happy to listen and I'd like to also learn from you. But if there's no like the topics in each week, and I just want to share the note regarding those two topics, L2 estimate and complex Monge-Ampere equation for both elliptic and parabolic approaches. Those are all used in Uyao theorem. And what else I should say? So even we assume Taylor manifold is already some of the classes of the bounded like the domains. So this are already very interesting, like the hard enough. So classes of bounded domains. I'm not even sure that I should put this assumption. One can replace this by the Kobayashi hyperbolicity and some, but let me just safely just call it by bounded domains in CM. So naively, if I naively draw, so let me just assume all those boundaries are just smooth for the simplicity. So there's a strictly pseudo-convex, which are already studied a lot. So this class, and also there's a class of so-called finite type, maybe probably here. And here is a complex hyperbolic space like this. And also there is just a convex domain. I think it could be something like this. So there's a so-called C linear convex. I don't know how to draw this diagram. Probably something like this. Something like this. And also there are also other types of domain. So it is very interesting to study these classes in terms of the KE.
Another class of domain is balanced domain.
I'm very afraid of like drawing the diagram correctly. So balanced domain. So and so on.
It's okay.
Chi, gamma. For each classes, I mean, the reasonable estimates and comparison, equivalence, and so on are already highly non-trivial enough. And what I actually want to look at specific domains with Ellen was the Hartog's triangle, because we have some already observation that previous known result does not apply directly. So that's also good to look at, especially for the fat Hartog, like the triangle is actually I want to look at for my research as well. So this is also good topics. And I'd also want to talk just one last thing for today because Josephine joined today. So it's also good to look at CR geometry. What's the reason? So the CR geometry guarantees that if you have complex hyperbolic space, then this is real 2 n-dimensional manifold. So if you look at so-called the CR boundary, for here, topologically, this is S2n minus 1 Riemannian manifold, but we equip with the CR structure. So this is actually CR sphere. So the important like the questions is that if omega 1 and omega 2 are biholomorphic, then boundary of the omega 1 and boundary of omega 2 are CR isomorphic. Converse is the reason like the question. And even for the complex hyperbolic space, I don't think this like the converse is well established yet. So people all believe that if the CR, I think this already the result is always the state is negative. It's not possible, especially for complex dimension 2. So the known like the situation is for the higher dimensional case from complex dimension greater or equal to 3, if the CR boundary is isomorphic, then the corresponding interior should be biholomorphic. People want to prove it, but this doesn't work for complex dimension 2. If the three-dimensional CR manifold is isomorphic, the corresponding like the strictly pseudo-convex domain are biholomorphic and so on. So this is also interesting like the direction to investigate in a sense that in this like the theorem. So this is complete manifold, meaning that we kind of neglect the ideal boundary. However, if it imposes the CR boundary on this complete manifold, then we can also say so regarding this like the big like the theorem and big conjecture. So if any of you are interested in like the CR geometry, then I'm also very happy to talk about the CR geometry, like the ingredients as well. So just one thing. So this is the compactification. I should say CR compactification of the Heisenberg group. So as we regard the sphere as a compactification from the Euclidean space. So if you want to impose the CR condition, so meaning that the complex structure is continuously extended to the boundary. So in such a case, we should not compactify the Euclidean space, but we should compactify the Heisenberg group. That gives the CR sphere. That is the ideal boundary of the complex hyperbolic space. So this business is also correctly related to the understanding geometry of the interior. So this is what I'd like to tell. So for the like the seminar, this like the summer. So if any of you have any like the opinion regarding your own presentations or some research like the ideas, I'm very happy to discuss without the record, or I might edit some of the like the sensitive like the conversations. Otherwise, what I'd like to do, I try to explain what's the motivation. I think we need to study the details of the L2 estimate and complex Monge-Ampere equation and try to look at the implication, what we can tell in terms of the invariant matrix. And there should be further possible implications too. It's worthwhile to also investigate. Yeah, this is today I'd like to just share the big like the picture I had in my mind and the note I shared. Let me just explain my intention. So as the note of the Lampert theorem that you are able to find from my website, so I just start from the basic setting that I already explained in this like the seminar, so that you can just look at all like the calculation perspective, so that all those can be tracked nicely, in my opinion. Then it gives you, so I assume some of you are not familiar with the Riemannian geometry yet. So if you try to follow the computation, then you might start with some of the pieces, even you use the ChatGPT or reasonable references, then I can clarify them together, of course. Then by just understanding each of the objects here, then you can understand the origin of the Calabi-Yau, like the conjecture and complex Monge-Ampere equation, why we concern this like the specific PDE, and what's the like the magic of this like the fully nonlinear like the equation, and what's the spirit of the Calabi-Yau conjecture. This also brings lots of interesting direction in complex geometry and the basic like the idea how to prove the like the Calabi-Yau conjecture from the elliptic like the method, continuity method, and the implications. So you can just look at this note to really get just a basic idea of the studying complex Monge-Ampere equation. And if you just look at each like the classes, all those like the concrete like the setting and the estimate could be quite like the subtle to really like the starting like the interesting estimates. Yeah, this is today I want to share. So if there is any other questions or comments, please let me know. Otherwise, let me then stop to record and we can discuss a little bit more freely.